Hello, and welcome to join me to follow the chapter 1.3 regarding crystal structure determination on our course in solid-state physics. And I think I will divide this 1.3 chapter into 3 different lectures. So I think I will first cover the 3 first, and then I will leave the second and third parts for the later lectures, because I think we will have too much of things to cover in a single monologue lecture we have. So I will first cover X-ray diffraction, Bragg theory, and speak up of lattice planes and Miller indices. So this will outline you the basics that we need to understand how can we make X-ray diffraction and what it means, and when we do have diffraction peaks and what they physically mean. So we will first start by motivating you X-ray diffraction, introduce the simplest of models, Bragg theory, and then speak of Miller's indices. That is essentially a way to characterize what's a lattice plane, and the rest will be left for the upcoming lectures. So I will start by just outlining very briefly that what we will be covering here. And the first thing that we should remember during these lectures is that the experimentally characterizing what is exactly the crystalline structure in question when we are looking at a specific solid, this is a kind of number one question often in solid state physics. In order to understand the properties of a solid piece of a material, and we are now equating solid as a periodic structure, a periodic material, we really need to know what is its crystalline structure to appreciate its properties. If we want to calculate, we want to understand something of the properties, we must know what is the crystalline structure. So this is the kind of starting point. Another way of hammering you with the importance of X-ray diffraction and structure determination is that over 50 Nobel Prizes, not just in physics, but also in chemistry and medicine, have been already awarded for development of techniques that can be used to understand the crystalline structure of different solids and materials. And this is a very important. So development of techniques and similarly using these techniques to determine what are the structures of specific substances. And I will have a table at the next slide showing you an example of these prizes. So one specific case, for example, is that we may use crystalline structure determination techniques, mainly the X-ray diffraction, to understand chemical and biological structures. And for example, I could go to the northern campus of our university, Tampere University, and then I could talk with a person who is on the medicine department, and they might be, for example, doing research on different pharmaceutical compounds. And those are the people who are actually maybe using a lot X-ray diffraction in their research and work, because you need to understand what is the structure of your pharmaceutical compound. And these are the only ways that you can really well describe them. So you need to crystallize your enzyme, your molecule, your protein. And once you do that, then you can actually shine X-rays or electrons into your piece of a material, and then you can actually characterize the three-dimensional structure. So this is very important. And not just in physics, but also in chemistry and biology. And in biology, it's becoming more and more important, because there are very complicated structures, three-dimensional structures, and it's not easy to characterize them, like what they actually are, but it's very important. Like a historical example, and this is a very famous example, is, for example, the molecular structure of DNA. So a Nobel Prize in physiology or medicine was awarded in 1962 for James Watson, Francis Crick, and Maurice Wilkins, for their discovery of the molecular structure of DNA. And sadly enough, Rosalind Franklin was not awarded of that time. And that's very sad, but I guess that reflects of what has happened in the history of mankind regarding equality of different people. So here's then the table I promised to show you, and this is not all the prizes, but at least a pretty good representative pick of Nobel Prizes that are related to X-ray crystallography. And as you can see, there's a lot of them in here on the list. And starting, the first ones were Nobel Prizes in physics. And Röntgen was the discoverer of X-rays. Max von Laue discovered that we can actually do X-ray diffraction from crystals, and that there is a kind of order in the X-ray diffraction patterns, and that then implied that this can actually be used to understand the structure, understand the order of the crystals. And then the father and son of Bragg family used X-rays to determine the crystalline structures, and then after that a lot of chemistry and medicine related physics prizes have been given at the regarding to X-ray diffraction. And here, the Nobel Prize in Graphene 2010, so from to Game and Novosel, was also verified. That's a graphene by using X-ray crystallography, X-ray diffraction. So this is our motivation for these upcoming topics. So it's really important in many cases to understand what is the structure. And if you want to experimentally characterize the structure, then you need some tools. And these we will be covering in these upcoming lectures. So X-ray diffraction is the main thing that we will be covering. And why we will be focusing on this is that it's by far the most important of techniques. There are other techniques. For example, we could do electron diffraction. So instead of shining Röntgen rays, we shine electrons in our piece of a material we want to characterize. We could also use neutrons. And if I recall correctly, neutrons can be used to characterize the magnetic domains. So if you are working on magnetism and trying to understand how different kind of magnetic domains are being formed. So for example, if you want to distinguish, is the type of a structure, is it ferromagnetic or anti-ferromagnetic, then you may need to use neutron diffraction because you need some way of seeing the spins of the structures. And you could also do atomic force microscopy. So this is especially important if you study interfaces and surfaces. So for example, recently there has been a huge surge towards studying two-dimensional materials. Recall the 2010 Nobel Prize for discovery of graphene. After that, the field has exploded. So atomic force microscopy is now a lot often used tool, especially when you're dealing with 2D materials. Scanning tunneling microscopy is another example, and with 2D materials, those are being used. And there are also hybrid techniques. And with hybrid, I mean that we are using both photons, so X-rays and electrons. And either it might be that we're doing mainly electron diffraction, but we're also then detecting photons, or that we would be shining photons and detecting also electrons, or we would be shining with both. And kind of one way of saying that why we care of these kind of hybrid techniques is that especially if we would want to understand phonons and if we would want to characterize a phonon distribution or dispersion relation of phonons in a solid piece of a material. And phonon is a quantized unit of atomic vibrations, how the lattice vibrates. Then we would need to use these kind of hybrid techniques. And in a way, how we can understand this is that we need to have a technique where we can, part of our energy that we put in is being absorbed by the material. And it's being absorbed due to the fact that we have these phonons present in the material. So those phonons absorb part of the energy that we are using to investigate the structure. And then when we can measure this kind of energy difference, then we can appreciate that there's some phonons are being excited. And when we do things right, we know that in kind of like which are the directions in the lattice that are important. And when we can do that, we can figure out the dispersion relation of phonons. But more of this in the later chapters. So when we are going into the mechanical properties, when we introduce phonons, and even after that, more specifically when we go to the thermal properties of lattices, because there we are more looking into phonons, and we are like developing a simple model to understand the 1D case of a phonon dispersion relation. But I just wanted to mention to you that these other techniques, they may also be used and will be used. And if I don't remember to mention these when we are like actually covering phonons and the dispersion relations, hopefully you now remember that these are actually related. But now back to our topic, X-ray diffraction, and let's now proceed in kind of going with the basics regarding that. So the assumptions we make in our upcoming treatment is that we assume that a so-called kinematic approximation is valid. And what this means physically is that we assume that the electrons scatter only once from our piece of a matter. So they just like once they scatter and that's it. And we don't need to worry about kind of multiple scattering processes. Another thing that we assume is that our Röntgen ray source or electron source, I think I should have a X-ray source here because we are focusing on X-ray diffraction here. And the detector of X-rays, they are far away from our sample crystal. So that's what we assume, and that's what in practice is often the case. And certainly when we are making devices, we can force this assumption to be valid by just designing the distances to be large enough. And what this enables us to do is that mathematically we can then treat the input and output waves as plane waves. So graphically, I'm showing this here so that we have a X-ray source or a electron source, that black dot there in the figure. And then when we go far away enough of this source, then even though the wave front, the phase front, where we have the constant phase of this wave, even though in principle it is curved, we can approximate that far away enough, this wave front is actually flat. And then we approximate that we don't need to deal with spherical waves or more complicated looking waves, but we can just be happy in working with plane waves. And then when we are dealing propagation of waves, like plane waves mean happiness because the mathematical treatment is so much easier. But of course we could complicate things by using something more complicated, but in the end, conceptually nothing would change. It just distributions would get blurred due to the fact that we actually have several plane waves propagating in different directions. Now we are ready to go into our subchapter of 1.3.2, and we are now discussing what's a Bragg theory and what are the main things to know about regarding it. So, what we do is that we are now considering a reflection of incoming X-rays, and we are considering a reflection from a flat crystal planes. So this is the kind of picture that is very, very commonly used when we are describing Bragg theory. So that instead of like imagining that we have lattice points and atoms in them, we are instead like imagining that we have some planes, crystal planes, and then the incoming X-rays, these blue rays here can reflect from these different planes. And then the kind of my main variables of interest is the scattering angle or incidence angle. And incidentally, this is defined differently than in like optical diffraction, where we have in diffraction gratings and in reflection, we actually have the theta, the incidence angle defined with respect to the surface normal and the incident ray. And in here, we are actually defining the theta, the angle with respect to the lattice plane, and the incident ray. So please be careful of the difference between the definitions. And then we have the D, the separation between lattices. And then this Bragg theory is a special case of the more general Laue description. Remember, Laue was the person who was also awarded a Nobel Prize in physics early on in the 20th century. So this is the kind of like a simplification, but I think this is a good starting point, because usually it's better to go in different topics and better to learn one bit, simple bit at a time, and then slowly generalize the treatment to the full case. So that's why Bragg theory will be covered first. And like I said, we are assuming that we have a collimated incident X-ray. So in essence, a plane wave. And what we are also assuming here that we have a monochromatic incident beam. So just a single energy is associated with the incoming photon. But this is, of course, just to simplify the treatment for now. And the scatter beam is specular, so that means that the incident angle and the scattering angle in Bragg theory, they are equal. So this is still the kind of scattering we are considering. In the more general case, the Laue description, that does not need to be the case, but more on that later. So what may happen when we have exactly the right kind of separation between the lattice planes D and when we have the right incident angle is that we may have constructive interference occurring between the nearby adjacent scattered rays. So at specific measurement angles theta, constructive interference occurs for the reflected rays, and this is what we may have measure. And this occurs when the optical path difference between the subsequent reflected rays is an integer of a multiple of an incident wavelength lambda. So basically, when this difference here, or 2 times this, sorry, just once this, no, it is 2 times this when it's equal to the integer of a wavelength. So basically, when we are imposing this and we are doing the math that is related, we end up with a Bragg condition, and mathematically Bragg condition is that we have integer n times lambda, the incident wavelength of our X-ray, times 2 times the d, and d is the lattice constant, the separation between the two lattices of interest, and then we have sine of theta. So n is an integer, and d is the lattice constant here. So this is a Bragg condition, and this tells us when do we see a diffraction peak. In practice, the X-rays penetrate very deep into the crystal, so thousands of layers can contribute to the diffraction. And what this means is that, in fact, the diffraction peaks are very sharp, so that even a small change in the scattering angle, reflection angle, even a small change makes the constructive interference to disappear, and we don't have the diffraction peak anymore. So this is the kind of the physical reality that happens in experiments. But in a way, it's an advantage, because the more sensitive measurements can be done, then more accurately one can estimate what is the lattice constant d. And please recall that this behavior that we are seeing here is very similar to what we have encountered already in optical diffraction gratings. Just recall that we are defining the incident angle and the reflection angle differently, but otherwise this is exactly the same kind of treatment. So what we have and what we can do already with the Bragg theory, and this is the only thing we will do in practice, is that we can now estimate what is the upper limit for the wavelength. And this we can find by just using the Bragg condition. And how we do that is that we just place the smallest integer we can imagine, so n equals 1, to the equation, and we note that the largest value of a sine theta that we can get is 1, it's unity, and these together result that the Bragg condition that is equal to this scene turns into a case that the lambda must be smaller than 2 times d. So this is the case that we can get out from the Bragg condition already. And this is the upper limit for the wavelengths. And recalling that for a crystal structure, the lattice constant is of the order of an angstrom, so about 0.1 nanometers. We see that the wavelength of incident photon must be quite small. So this then means that we must use X-rays if we want to do X-ray diffraction. We cannot get access to this information if we would, for example, shine a light into the structure. Then we do not see these diffraction peaks, but we just need to use small enough wavelengths. And then strange thing about this Bragg condition is, or it's not strange, but right now it's strange that it works for all possible periodic planes that we have in the lattice. So in the picture in the previous slide, we just draw a single lattice plane, and a lattice plane is a plane that is going like through the different lattice points, 3 collinear lattice points, and through them, and that's enough. That defines a single lattice plane. There's actually a lot of those in any of crystalline structures, and the Bragg condition works for all of them. So we kind of see right away that we must somehow be able to generalize our treatment, that we could also like understand the other planes in question. And this is what we will do next, but we will need to make a little bit of a detour from actual X-ray diffraction into these concepts, that how do we define these different lattice planes. So a general side note, later on we will also learn that these properties of a crystal depend on the crystal periodicity. So this is also important when we are looking at other chapters. So this is not an important point only when we are looking into X-ray diffraction, but only this is important. Also, this is important when we're looking at, for example, the thermal properties of the lattices and the electronic properties of lattices. But what we must do next is that we need to come up with a way to define a lattice plane, because that's the way how can we then generalize our treatment from the Bragg theory to the more general Laue description. So this is what we will do then next, in the next final part of this first part. So we will go into the section 1.3.3, and now we will be speaking of lattice planes and Miller indices. So we are considering a Bravais lattice, so a periodic lattice, and this is being spanned by the lattice vectors. And the lattice vectors were A1, A2, and A3, using our notation we have already used. And now a lattice plane is like any plane that contains at least 3 non-collinear lattice points. So this is a way how do we define a lattice plane. So you must draw a plane, and at least 3 different non-collinear lattice points must be like, we must go through them. We must intersect at least 3 different non-collinear lattice points with our plane. And if that happens, then we have a lattice plane in question. And we are focusing on Bravais lattices. So this is a picture that hopefully like elucidates what happens. So for simplicity, I'm drawing the different lattice directions A1, A2, and A3 as X, unit vector X, and unit vector Y and Z, because maybe that helps to kind of understand what happens. But of course, the same approach works for a more general lattice. So A1 need not be X, and A2 and A3 need not be orthogonal to A1. But this is the simple scenario, so let's focus on this. So we have a plane, and if a given plane is intercepting these axes AIs at the, for example, in the case of the picture, now it's intersecting the axis A1, so x-axis at point unity. So at the first lattice point away from the origo we have defined. The same way it takes place for in the y direction. So the plane intercepts the A2 vector 1 lattice constant separation away from the origo, and here it doesn't intersect the axis A3. So we say that it intersects the A3 at infinity, and this is how we have defined our plane. And what we will do now is that we will come up with a way to use a notation that describes this plane that we have drawn into our lattice. And later on, we learn that this choice for the description is very useful because it is very explicitly compatible with the Laue description of X-ray diffraction. So when we use this notation, how do we define a lattice plane? It becomes explicitly clear that when we are seeing a diffraction peak. And hopefully I can make it clear to you in the upcoming moments. Now, what we do is that we take the reciprocal values of these above numbers. So 1, 1, and infinity. And the reciprocal values are 1 over 1 is equal to 1, and 1 over 1 is equal to 1. And then we have this 1 over infinity, and that we just equate that's 0. So we're not mathematicians, so we're just perfectly fine in saying that this is equal to 0. The smallest integers having the same ratio that we can imagine, and this is now that we must turn these values and these 3 numbers into a set of smallest possible integers, and then we are having our final indices. So smallest integers that have the same ratio are 1, 1, and 0. So we don't need to do anything for this choice of a plane. And then we can describe this plane of interest with this index set. Sorry. And now we can describe that this plane is actually described with this kind of index set. Sometimes we need to come up a way to describe many planes that are parallel to this, and then we could use a notation when instead of an ordinary parenthesis, we would have square brackets here. And that notation, if I remember it correctly, then corresponds to a family of all the planes that is parallel to this single plane. So then we would have a family of planes, and then if you would think, for example, a Bragg theory, we actually see the diffraction peak to form by constructive interference for many planes. So that's a bit of a notation. And these indices are known as Miller indices. This is the term you should memorize and remember for the rest of the course. And maybe for the rest of your life. Why not? Let's now go through different examples so that we kind of via repetition we learn that what are these Miller indices and how do we form them. So let's take another example of this protocol we have just discovered and introduced to understand what are the Miller indices. So first of all, we find the intercepts, and now looking at the figure, we can see that we intercept the direction A1 at a value of 1 over 2. So just here, we are not intersecting it, we are intersecting it midway between the origo and the first lattice point along A1, X here, and this is why we have 1 over 2. Then the y-axis is being intercepted at position 1. And then again, we are never intercepting the z-axis, so we are intercepting it at infinity. Then what we do is that we calculate the reciprocal values. So 2 over 1 is the reciprocal of 1 over 2. And then 1 again is the reciprocal of 1. And then we have this 1 over infinity. So that we get the reciprocal values. So what we have is that we have 2, 1, and 0 as the indices. And now the final third step that we should do, and we will do it, is that we will multiply to make the smallest possible integers. And now all of these already are integers, so we don't need to do anything. So what we have is that we have the same indices we just figured out. And later on, by the way, we discovered that there's a more elegant and informative definition of the Miller indices. And that's why these are so useful in terms of X-ray diffraction. But more of that later in the next lecture. And then yet another example. So now we have this kind of plane, and then instead of drawing a rectangle, we're now drawing a triangle, because we are only working in the cubic cell. And let's discover what are the Miller indices. And again, what we see is that we are intercepting. Okay, actually I have a mistake here. It should not be intercepting the axis A3 at infinity anymore, because clearly we are seeing that we are intercepting at value of unity here. And the reciprocal values of unities, of course, they are unities. So what we have is that we have an index set of 1, 1, 1. And then the final step would be that we would multiply to make integers, but they already are integers, so we don't need to do anything. So this is an example. And then the final example, that is that we consider a slightly elongated triangle. And this, please pay notice, something actually now changes with respect to the previous examples. So intercepts are now 1, 1, and 2. And we calculate the reciprocal values, and they are 1, 1, and 1 over 2. Like this. And now the final third step actually starts mattering. So we must now multiply to make the smallest integers. And since we do have that 1 over 2 there, we must multiply to get rid of that. And now we end up with an index set of 2, 2, 1. And this might surprise you in the beginning. So how come these first indices 1 turn into 2s? But this is the procedure, and we are just mindlessly following it. So nothing surprising here in the end. But please remember this, that this is where complications and errors start arising, when we have these slightly more complicated looking planes. So please pay attention to this difference in this example. And a moment regarding terminology. When we have a plane intercepting the axis at a negative value, and that's also a possibility, we should be careful regarding our notation. And then what we do is that then we modify the notation, and instead of indices of minus 1, 1, 2, we write the minus on top of the index. So we use this kind of like a notation where we have the bar on top of the figure that is actually now negative. So this is the terminology that is being used in Miller's indices. So these are now the ways that how do we define the different lattice planes. And please remember that the Miller indices are a way to characterize them. And we are focusing on understanding X-ray diffraction. And we will soon learn that these are actually highly useful and actually very, very useful to describe lattice planes using this way. But thanks for you to listen. And I think I will stop here, and I will follow up in a second part of our lecture. So thanks for listening. Please take a small break, and then let's follow up on the upcoming chapters. And we will now then learn more about the X-ray diffraction. So thanks, and bye-bye.